today I'm going to be telling you about kernel representation. This is going to be all about how we're going to adapt our kernel representation incrementally in a continual learning setting. And I'm Martha White, if you've never met me before. So completely unrelated to what else I'm going to tell you in this talk. I'm going to quickly tell you generally the type of research problems I've been looking at, because we'll probably end up working on things together and you might be interested in working on some of these things yourself. So these are all some of the areas I've been looking at lately. I've looked at a lot of off-policy policy evaluation. A lot of my algorithm development focuses on how can we get low computation complexity, how do we get algorithms that work well in practice. It really drives a lot of what I do. So off-policy policy evaluation, and then related to that is multi-step time series prediction. They're both looking at temporal predictions. Exploration, I'm looking a lot more at exploration lately, and representation learning underlies a lot of what I do. So I'm looking at dictionary learning, matrix factorization, predictive representations of GBS, and today I'm going to tell you most about the last one, kernel representation. So this paper is a paper that's in ICML. This year it's up on my website. If you want more details, you can go to that paper. And today I'm going to try to get you kind of excited about the problem, what's interesting about it, and a little bit about what's new that we've brought to it. So in the end, I'm going to show you an algorithm that's kind of new, and hopefully so the problem that I'm looking at is a continual learning setting. We have an agent, it's interacting with the environment, it's getting a constant stream of data, and this is always going to change the way we design our algorithm. So a lot of kernel representation building algorithms look at fixed batches of data, and so we're going to start rethinking how we design some of these algorithms. And so in this setting, more generally, an intelligent agent needs to build up our representations. And this word representation is a little bit of a vague word, but what I really mean is we want to re-represent or transform the input observations that the agent is seeing, and we want this transformation to facilitate learning. Again, facilitate learning can mean different things for you. Maybe that means that you learn faster or you learn well in new problems, but in general this is a slightly higher level goal behind representation learning. And so we really need to think about how do we do that re-representation to facilitate learning. Okay, and one such representation are kernels, and kernels are really a pretty powerful representation. They've been looked at for a very long time in machine learning, and they're a very intuitive representation. So the idea behind kernel representations is that the features that we have consist of similarities to some prototype observations that we have seen as an agent. So we might ask how similar am I to something I've seen in the past. If I know how similar I am to that thing, and I know what happened when I saw that observation, then maybe I can infer a little bit about what's going to happen for this new observation. So this talk is largely about 4 kernel representations. One of the biggest questions is how do we actually pick these prototype observations? And so we're going to talk about how we're going to pick those prototype observations and what are the challenges in doing that. So I'm going to kind of give you the takeaway of what you should take away from this talk before you even really know what all the things mean. Hopefully it'll frame a little bit for you why I'm telling you what I'm telling you. So really, I kind of want you to take away these 3 things. Carefully selecting prototypes is important. So it can really make you learn a lot better if we more carefully select our prototypes for these similarity-based representations. Given that we really do care about selecting our prototypes carefully, we start thinking about what methods let us do that. So there's a really big literature on selecting representative items. You can imagine many people have wanted to solve the problem. Given a set of items, how to sub-select a set of useful items. But there's actually not a lot for continual learning. So it's a really big open question, I think. Sometimes it's a fun question to tackle for the continual learning setting. So I kind of want to get you a little excited about that. And the last thing I want you to take away is that the online submodular maximization approach that we take, I think is a really nice direction for getting robust algorithms that work pretty well in practice and have some nice theoretical guarantees. So careful prototype selection is useful, and the way that we do with online submodular maximization, I think is actually a pretty great algorithm that we've seen works pretty well. Okay, so given that that's kind of where we're going, I want to start a little bit further back. I want to more clearly tell you what is a kernel representation in terms of the similarity type of representation, and a little bit more why you should care, mostly why you should care. Okay, so kernel representations look a little like this. They look like this pretty simple linear weighting of similarity features, so it's a little like a similarity basis. I'm not going to reveal these pictures now. So our features consist of, for some input observation x, our function or our prediction is going to be a weighting of some similarities to prototypes. So here's Z1 all the way to Z4. So we'll have B prototypes, B being our budget size of prototypes that we can have. And our features consist of these similarity values. Okay, so we had some input observation X, we get 4 features, and we learn these coefficients W on those similarity values. Okay, that's really what our kernel representation is going to look like. So a very common similarity value here was saying how similar is X to some prototype I have seen before, Zi, is really these Gaussian kernels. Gaussian kernels are likely the most widely used similarity measure. But one of the reasons kernels are really nice is that we can replace that K with lots of different similarities. So I'm going to give you just one more example of what a kernel similarity could look like, so you can kind of start to see the space of possible functions that we can learn. Okay, so imagine we don't even really have real valued observations. We have observations that are things like age, gender, income, education. It's not as easy just to say throw this into our standard machine learning setting. And maybe your goal here is to predict how many hours this person that's defined by these attributes works per week. Okay, so we're not just going to do something like a regression on this, but if we use a kernel representation, we just have to define a similarity measure between, say, an input observation X, so some person X1, and how similar they might be to some person X2, which might end up being a prototype that we think usefully represents the different types of people that we might see. So a very simple similarity measure here is just matching which categories are actually the same. So both of these individuals are female, they're both have medium income, and they differ on the first and the last categories. So their similarity out of 1 is 50%, so 0.5. It's a very simple similarity measure, but it does take nicely all this different type of inputs that we could see, like age and so on, and it converts them nicely into real values. Now all of our features are, again, real values. So that's generally what kernel representations look like, and it kind of leads into why I think that they're a really good approach for defining our features. So one thing that's really nice is that we can define all these different specialized kernels that give us a lot of flexibility in what we can model. So we've already seen some kernels for things like that matching kernel, but there's these nice convolutional kernels for images, there's string kernels for text and gene analysis. There's this whole array of different kernels that people have defined, experts have defined, that can be useful for different types of data. So that's one really nice thing about them. They have a lot of theory behind kernel representation. There's nice universal function approximation capabilities. So once we have our kernels, once we actually pick our prototypes, which is, that's asking a lot. Well, once we have some of that done, really we're going back to our linear estimation problem. We're trying to learn those weights W. We have lots of really good algorithms for that. And the last one I like a lot about kernels, actually, but I feel like it's not talked about as much, is that they're a pretty interpretable solution. So when you look at why did my function predict what it predicted, you can actually look at what you were similar to and infer a little bit why you may have predicted that you're going to work this many hours a week. Because you look similar to this person, and they work this number of hours a week. So even often when you look at these big neural networks and you start looking at their hidden layers, it's a human tendency to say, hey, this hidden layer kind of looks like a dog. That kind of makes sense to me now, why this is predicting what it is predicting. So by having these prototypes, it's a lot easier to kind of look at what we're predicting. I like those reasons. Okay, so at this point I could just say, this is a short talk, we only have so much time to talk about why you should care about this problem, and I think I only have 10 more minutes. But, so instead of just jumping right to how are we going to solve this problem for prototype selection, I want to motivate just a little bit more why we should care about doing this optimization carefully, or why we should start caring a little more about how we're going to optimize these things. So a natural question is, do they work? So I told you a little some motivation for why I think they're important, but really one of the reasons you might be skeptical is you don't hear about people using them that much. Everyone's obsessed with neural networks. They're not really using kernel representations as much. So this is, I think, a pretty natural question. And why aren't they used more? So there's definitely some nice results out there showing, big labs taking shallow representations of kernels and getting really impressive performance. But there's only, I can probably count those on my hand. So they really aren't used that much. And one of my hypotheses for why this is the case is that we just really need more optimization advances for these types of models. We have, for neural networks, we've had all this increased availability of data, which has been a good explanation for why they're working well, but I think they're also working a lot better because of optimization advances. So, the basic optimization algorithm for neural networks is still largely gradient descent, but there's all these nice things that people have learned. What kinds of heuristics to initialize your neural network with, what kinds of structures we should use so that we can actually get gradient descent to work really well. So all this human search hour has gone into taking neural networks and getting them to work well. And so I think we can actually make some more advances using kernel representations as well. If we take somewhat similar human search hours and start asking how are we going to get our kernel representations to work really well as well. So I really want to focus some of the work on how are we going to get optimization improvements for these types of representations. So I want to highlight that this is an important question, and it's a question that has not been ignored. Of course, many people have been working on how do we learn better with kernels, how do we select prototypes, how do we pick our kernels, and particularly the Gaussian process community has been doing a lot of work on this. But this comes back to my point that there has been a lot less done in the continual learning setting. So the setting where we imagine we have this lots and lots of data coming in. A lot of the algorithms for Gaussian processes are somewhat expensive. They're at least quadratic in the number of prototypes, often more. So they're usually for fitting smaller data sets and for a very expert-driven setting. So just like we want to scale with data with neural networks, I think we really need to focus on fast incremental learning algorithms for kernels, and then maybe we can start actually finding ways to get these types of models to work really, really well on big data. Okay, so with that reasoning for why this is the kind of problem I'd like to solve for kernel representations, why I care about prototype selection, let me specify the question just a little bit more clearly. So my goal is how are we going to select prototypes in this continual learning setting where it's robust and easy to use for a non-expert. So we've figured out some of the heuristics and optimization settings we should use so that other non-experts can start using these models as well. And it really needs to be with low computational complexity so that per step we're able to process efficiently. And this means that it really needs to be linear in the number of prototypes. Okay, so I'm just going to assume that this group is okay with why it should be linear in the number of prototypes. And I'm just going to continue on to why does it need to be a careful selection, and then I'm going to tell you a little more about the algorithm. Okay, so one thing you could say is, well, kernel representations might be great, but why do we have to be so careful with selecting prototypes? I'll give you a really simple algorithm. Randomly select prototypes, and they're going to kind of cover your space. Uniform random is usually robust to different things. So in practice, actually, that does work okay sometimes, but some of the time there's some failure cases. This is one time series data set we have in our paper. It's a laser data set, so this is the intensity of the laser, and there's these intensity collapse events that occur. So for this data set, if you take 300 random prototypes, and then predict out to this time steps of 100, it is able to actually predict really well. There's a lot of regularity in this data set, so it can actually predict quite well in this time series. But when there's a collapse event, this is the collapse event for the purple line, the regression solution using random prototypes does not work well at all. So it continues to think that it has this oscillation. But if you take the exact same regression algorithm and you just a little more carefully select centers so they more cover your space, you're actually looking at these different rare events, then you can actually model this collapse event. So in some cases random works great, but really in other cases it fails drastically. So we want to make sure we're covering our space well, we're really modeling our space and using our budget size as effectively as possible. Okay. So Richard, monitoring that time I have.
6.5.
Good. Okay, so this is just one result from our paper about how we're going to do this selection. And really the key is we improve a little bit in terms of regression performance, but what we improve the most in terms of is how efficiently we select these prototypes. So assuming you're on board with that we need to select prototypes carefully, my focus is now going to be on how we're going to do this efficiently, linear per step, which really there are no algorithms that currently do that. Okay, so there are lots and lots of different approaches that we could have taken. In fact, we looked at all these different ways that we could possibly go. And I'm not going to be able to tell you about all these approaches, but each of them is missing something that we need to really satisfy all of our requirements. So you can look at the paper, you can come talk to me about what these things are missing. But there's really this nice community of people who work on streaming algorithms. We look at processing big databases, and it's very related to the continual learning setting, but they usually have big databases that are fixed, and they're allowed to go over those databases multiple times. So there's a natural chance to take some of their algorithms, bring it to continual learning, but acknowledge that we can't actually pass over our data multiple times. You know, we're going to always see new data. We're kind of throwing away old data. But this community has some really nice simple algorithms, simple greedy algorithms and theoretical guarantees that are very natural for porting to continual learning. So this is really the direction that we took for this problem. So let me tell you about the general approach and then how we fix it a little bit. So our goal is going to be to solve this optimization problem. So this is really the optimization problem. We have to care for prototype selection. So S is the set of prototypes that we're going to select. X, this mathcal X, is the set of all possible observations that we actually see. And we need this set S to be no larger than B. B is our budget size. Okay, and G is some criterion that's measuring something about how useful our set is. Usually it is some kind of diversity criterion. So you want a diverse set of prototypes. They're going to cover your space, but there's other criteria that are discussed in the paper as well. Okay, but for now we're just going to assume G is some set function that we would like to max out. We'd like to find the best subset X that's going to make this criterion as large as possible. Okay, this is an NP-hard problem. You know, whenever you have discrete sets of items, you subselect discrete sets of items, it's often going to be an NP-hard problem. But the nice thing about this problem is that the greedy approach, a very simple greedy approach of just saying on this step, if I were to add in this observation and replace the least useful observation, which is a very easy algorithm to implement, there's a nice theory that says that that's actually a reasonable thing to do. So you can get a good approximation error. It's at least half as good as the optimal solution. So it's nice that a simple algorithm that we can say that we would like to do the simple algorithm, and then the theory says doing the simple algorithm is probably the right thing to do. So the first thing is that the simple algorithm is great. So it's like I say, it's attractive and there's theoretical guarantees. But then there's these things that make it not particularly useful for continual learning. So it's very expensive. You have to actually add your point and remove your point and check each time was this a good thing or a bad thing to do. And like I mentioned, because it's from the streaming community, they want to do multiple passes over the data because it gives you a chance to reconsider. Should I have added this point? I didn't add it the first time, but maybe now I should add it now that I have more information. So these two things make it a little bit not suitable for continual learning, but we're going to be able to get around those two things. There is one algorithm that tries to do one pass of the data, and it does so by keeping a large number of parallel solutions and then deciding along the way which of those solutions it should pick. This is actually a pretty cool algorithm, but it ends up being a little bit slow because it keeps thousands of parallel solutions. So in theory, it's very nice, but when we implemented it, it was somewhat impractical, especially in terms of memory. Okay, so our solution was to do always the minimal work possible. We want to keep this greedy algorithm, but we want to justify that it is an okay thing to do for the continual learning setting. So we kept that same greedy algorithm, and we changed the requirements to not need multiple passes of the data, but rather to keep the same spirit of multiple passes. Now, for the continual learning setting, we need to say we need to visit parts of the space multiple times. So we don't need to see the exact same observation again, but generally we need to come to a similar part of the state space and see something similar to what we've seen before. And then all the theory can really go through the same way. And this really matches more what we expect in reinforced learning. We explore our environment, and then we continue to explore and see similar parts of the state space over and over again. We never see the exact same trajectory, but we see a lot of the state space over and over again. Okay, and I'm going to continue to the next one. So this fixes one of the problems about multiple passes, and then to make this actually more efficient, to avoid all these pairwise comparisons that we need to do, we can then drill down a little bit more specifically, and instead of generally considering the streaming optimization for any kinds of subsets, we can look at the structure in our prototype selection problem. So because of a particular structure, we had this nice locality that we can exploit, which again I failed to explain right now, but it lets us do lots of fast local computations. And we can reduce this computation from quadratic in the number of prototypes to linear in the number of prototypes. So it's all about keeping the same greedy algorithm, but making the step that was expensive in the greedy algorithm much more efficient by exploiting the structure that we have in our prototype selection problem. Okay, so let me just tell you a couple things about experiments. We went through a lot of experiments, mostly trying to see how much should our approximations actually give us approximations? What do we really lose for our approximations? How much runtime improvements did we gain, and what was our regression performance? So again, I'm not going to go through all these experiments, but I'll just highlight a couple things, one runtime result and one regression result. So this is our algorithm, this is the number of prototypes that we're selecting. This is block greedy, so this is the algorithm that we have. Full greedy means doing the greedy algorithm but not taking advantage of the block structure. And the C streaming algorithm is that algorithm I mentioned that has many solutions in parallel. Okay, so you can clearly see that the red line is scaling much better. It's maybe scaling at a lesser rate than we would like, but we didn't actually do a lot of optimization improvements when we implemented this algorithm. So it's really much more practical for implementation than any of the other competitors that we could currently use out there. Okay, and then despite the fact that it's much more efficient, for one of the data sets that we looked at, is able to do just as well as some of the other algorithms that you might use. One of the most widely used algorithms is kernel recursive least squares algorithm, KRLS. So we don't necessarily do better than these algorithms, but that's not really what we're expecting. We'd like to match what they can do, but do so much more efficiently. Okay, so to summarize, what do we really have this mean here? Why should you go look at this paper and then possibly implement this algorithm and use the algorithm? So the main new things are that we have this new algorithm that lets you pick prototypes incrementally that is linear in the number of prototypes per step, which is really, there's no other algorithm that will do that right now. We have what I think is a new strategy for looking at algorithms in the streaming community and bringing them over to the continual learning setting. So this idea of multiple visits to the space, this idea of covering your space, is not necessarily specific to just our prototype selection. It can be useful in general for other problems. And something I didn't get a chance really to talk about is that we also have to talk about what our criteria are. So we kind of start from the beginning and think about what should our criteria be for selecting prototypes in the continual learning setting. And so we have the space of supervised and unsupervised criteria, where some of the criteria that have been used before become instances of that more general criteria. Thank you. Sure.
Can you just go back to time chart, Pete?
Yes.
So you mentioned that this was now linear. Why is it still got an exponential curve?
Yeah, I agree with you. So that's what I was saying is that here, like you said, this should be linear, but when we implemented this, the implementation was not taking advantage of some of the things we could have done for the linearity. So this is scaling well, but it's not scaling as well as it should be scaling, and I think that's our core implementation. So our next step is really going to be to increase this budget size, see if it's continuing to not scale as well as we would hope, and then go and figure out what we have done wrong. Go ahead, Rich.
So the basic strategy is you're adding or replacing prototypes, things as actual input vectors or something as they occur.
Yes.
And trying to keep a nice diverse set. But what if you need a prototype that's not actually an observation, but maybe an idealized observation or something?
Okay.
Is that a limitation or?
That's a good question. So you can always and the Gaussian process regression community really looks at how do we select centers that don't have to be our input observation. They just like clustering, you're going to set things to be the mean, something that you may never even see. It's just something that is useful as a basis center. I think there's a bit of a philosophical, ideological question of should we allow our centers to be anything, things that we've never seen, and should we force them to be observations that we have seen? So all I can do is give you ideological answers. But I have reasons why I think selecting prototypes is a good strategy. It doesn't mean that maybe we wouldn't want to have both. I mean, you could imagine actually having something where you force some of your prototypes to be real things, you allow some of your things to adjust. So this is a discussion that we have for a long time. I don't think it's a limitation because I think it's actually a good structural constraint to force our prototypes to be things that we have seen before.
Good.
Go ahead, Chava.
I'm wondering about whether there is a real trade-off here in the sense that if you're fixing the budget size, then you necessarily are going to lose on accuracy, and if yes, or then like what is the trade-off, or like that would be
Okay, so first of all, is there a trade-off? Because we said.
right.
So sometimes there isn't a trade-off. In some sense,
There could be some easy problems. That's true. Like
so there can
some
be
easy
problems.
instances.
In some cases, reducing your budget size is like a form of regularization. So if you allow more and more a larger budget, then you start having situations where your system is unstable and you actually get worse solutions. So there's like this bowl where there's some optimal budget size. That's not as many things as you could possibly add. Okay, but in general, there's some intuition that the larger we allow our model size to grow, the more complexity we can have, and then we can use other methods to try to be robust to having pick too large of a model size. So I really believe there is actually this trade-off. We really want to make our models as big as we can, and then find more clever ways to shrink them afterwards, to regularize them down. But you said something, there's a second point you made too. Oh no, that was the only.
Can I ask Chad a second point? No, not a related point to Chad's question. So I know in the attribute or feature selection literature, you sort of have two approaches. One is you have like all the features in the world, and then you start figuring out which subsets actually work out. You start weeding them away. And the other is to start with a complete blank slate, and you add one and see if it adds utility and add another.
Right.
Like it sounds like this is more like it's not really subtraction, but it's starting with the glass completely full, or it's full with as many features as you can.
Actually, this would be the opposite approach, in my opinion. You start by adding them slowly, and you make sure that you never go above a budget size that you're willing to your agent to have. The other strategy would be you don't mind having a huge memory, so you just keep all of your prototypes since the beginning of time, all the observations since the beginning of time, and then allow your regularizer to self-select. You still have to store everything. I think for a continual learning study, it makes more sense to build things up.
That's good. So, and the one reason I went to attribute selection is because sometimes you get into a trap where you add a really good feature, it adds a lot, but the rank ordering of the features, like certain features may give you a quick win at the beginning and have a lot of utility, but in the end game, it's actually a collection of features. Each has a very small contribution to the overall utility that is the biggest win. And so sometimes, like let's say the best first rankers, when you go forward from a blank slate, you get stuck with these what appear to be really good features in the game, but you can't get rid of them. Is that a worry? Is that actually something you can?
It's a good question for feature selection, for particular. I didn't mention properties of this maximization.
Yeah.
It's a submodular maximization. So if it's a submodular function, it has this really nice property that has this diminishing returns. Feature selection is not exactly submodular, it's an approximate submodular function, and it has this property where, for example, two features together could significantly improve your estimation, much more so than each feature individually. And submodular functions don't allow something like that to occur by definition.
Oh, so then that's totally
so that won't occur in the same way.
That's super. Thank you.
Go ahead.
So there's not a good alignment between this graph and the next one.
Sure. You want me to go to the next one?
Sure. I mean, there's lines on one that don't occur on the other.
Yes,
so does that mean those other lines, those other algorithms are really slow?
So in this graph, random doesn't have any runtime. These ones were just a different part of a version of our algorithm that was easier to implement. But we wanted to see if there was actually this additional step that we added that was very important. It seems to be very important. So that runtime is actually similar to this runtime. And then KRLS is quadratic in the number of prototypes, so it would be very slow on that graph. But you're right, we could add it to the runtime graph anyway. And I should mention, KRLS doesn't actually allow you to fix your budget size. It has this very finicky threshold parameter that goes above or below the budget size. It's also a little bit hard to plot on this graph with increasing budget size, but we could probably figure it out. I think that's a good idea. Go ahead, Rich.
In the beginning, you talked about, you contrasted a gradient descent approach with a kernel or prototype approach.
Okay.
And I just wondered if you could kind of mix them a little bit, like you could take the prototype structure and then do gradient descent in those parameters.
I totally agree with you. So there's this nice part of the prototype selection. You could, for example, for clustering for Gaussian processes, they really do gradient descent on the means to start adjusting them to make them useful. You could swap out that smooth optimization problem. That's kind of this big non-convex thing, and you could replace it with this NP-hard discrete-like optimization problem. And it's not clear which is the right one to use. But yeah, definitely you could swap those two things in. You could you could use this to pick the prototypes and use gradient descent to adjust kernel parameters. There's lots of ways you could swap in and out optimization problems. Yeah, it's actually kind of interesting to try. Go ahead, Roshan.
So you mentioned that there were these multipass algorithms, and you don't want that, but you assume that you visit this same states multiple times. And does that help does that get rid of some of the problems like the DD selection problems? Like what are in the limit as time goes to infinity, what are the pitfalls that your algorithm doesn't fall into? Because it's visiting the same states multiple times.
Okay, I see. So it doesn't actually visit the same states, but it has to visit states that look similar to all the states that you need to see. Okay, so what ends up occurring is you build up this set of different prototypes, okay, and then when you come back for your multiple pass, you get a chance to adjust those things to better cover your space. Okay, and then as you do one more pass, you start to improve less because you get to adjust your prototypes a little bit more, you get to swap in a new one that was better, and now your improvement starts to decrease. You get to do another pass, and as you've done enough passes so your improvement is no longer increasing, it lets you guarantee that you've actually reached a point that is a point that's close to optimal. So you've stopped changing. Whereas if you only do one pass, you haven't really converged in a sense. I mean, if you were allowed to do another pass, you would actually get to continue to increase your maximization, and then of course you're not able to see how close you're at optimal because you haven't converged yet. So it's all about converging.
So you do have some sort of convergence that has to happen if you under that assumption. Like,
Yes, exactly. It has to stop changing at some point.
Okay, thank you very much.